Hi, everyone. Hello. Good morning, everybody. Welcome to Lecture 8 of DSCI 572. So in the last lecture of this course, I'm going to be talking about more advanced convolutional models. So far in the course, we have been discussing convolutional neural networks, how they work and why they're good at image classification tasks. And we also discussed a little bit about transferred learning, which is also something helpful to let us take advantage of the pre-trained models that are available to us and adapt them to the particular classification tasks that we have. In this lecture, we're going to take it a little bit further, and we're going to be talking about a special type of model called Siamese network in the context of few-shot learning, and also generative adversarial networks. So I think both of these are interesting applications of convolutional neural networks. I've changed the lecture notes a little bit. For this year, I've included few-shot learning instead of autoencoders because you are going to learn about autoencoders in one of your next courses. Okay, so let's get started. All right, so with image classification, so far the assumption has been that we have relatively large data sets in which we have hundreds of thousands of images per class. However, usually this is not the case for more practical applications. And typically acquiring more data is hard. Sometimes it's impossible. Yes, we can do something about it by implementing some data augmentation techniques, but that only gets us so far. It's not the solution. So, for example, think of a face recognition system that's implemented for a company so that they can authorize their employees to enter some of the buildings. So in that case, if we use a CNN, would it make sense to tell each employee once they join the company to, hey, just take 1,000 pictures of your face in different orientations, different angles, so that we can retrain our model and give you access to our buildings? This doesn't make sense. And even if we have those 1,000 images of each new employee, then every time that a new employee joins the company, we have to retrain the entire model in order to make the face recognition system recognize their faces as well. So this is just one application of a situation where the usual kind of data sets that we're used to just doesn't work for the task that we have at hand. Okay, so this is what a training set looks like. What we have had so far in the course. These are our training sets. We have different classes for each class. We have hundreds and thousands of images, and we can train a CNN to classify those images for us. However, if we don't have that many images in our classes, there is another technique, another algorithm that we can use, which is called few-shot learning. In few-shot learning, instead of training a model on a new class of images, which contain a lot of images, we use the similarities and differences of an image compared to other images in order to understand what class it belongs to. So it's a little bit different. The goal of a classifier CNN is to identify the classes. The goal of a model in the framework of few-shot learning is to learn the similarities and differences in between the images. Okay, so in this example that you can see over here, this is just a network, an example of a model that we have been working on so far. We have a test sample. We want to know what class it belongs to. So we already have a class for that image in our original training data set. That's a husky. So the model can identify that and classify that husky as belonging to that class. However, what if we have a situation where we have an image, like the image of this rabbit, but the training data set does not contain any rabbits? So yeah, at this point we might say, okay, we have to supply thousands of images of rabbits in the training set and retrain the model in order to adapt our model to this particular type of query. However, that's not practical. So we need to have a different model that can achieve the goals that we have here. So this image and the class that it belongs to does not exist in the training set. Okay. So few-shot learning is about learning to classify a new test image with only a few examples of that new class. So suppose that this is the test image, this is what we want to predict, but instead of having thousands of images of this rabbit, we only have one, or we have a couple. Okay, so in that case, we can use the similarities and differences between this rabbit and a collection of other images that we call support sets. And based on that, we can identify which class it belongs to among those new classes. So none of these classes that we call support sets exist in the original training set. However, if our CNN model is trained well, and we use the kind of reasonable models that are trained for this purpose, the model can figure out the similarities between the test example and those examples from other classes that the model has never seen. So the model could say, okay, this image, if I extract the features of it, it looks more like the image of the rabbit in that new set of classes rather than, for example, the beaver or the fox. Okay, so that's the whole idea behind few-shot learning. Okay. So, a little bit of terminology. So if in the new classes we have n samples per class, we would call that an n-shot learning problem. For example, if we only have one sample in the support set, we call that a one-shot learning. Okay? So you can imagine the support set being another training set. However, it's a training set with very, very few examples. And it's a training set that its classes do not exist in the actual pre-training set that we have trained the model on. Okay, so in this example, this is an example of one-shot learning, meaning that we only have one shot, one example to show to the model in order for it to tell us whether this image belongs to that class or not. Just one example. Okay, and also if we have k classes, we call that a k-way n-shot learning problem. For example, here we have a 6-way one-shot learning problem, meaning that we have to choose among 6 new classes and detect whether the image of this rabbit belongs to which one of those. Okay. In this other example, we have 2 images of the new classes per each class. So that's called a 2-shot learning problem. And because the model has to choose between 4 different new classes, we call it a 4-way 2-shot learning problem. Okay. Cool.
Will just be choosing among the new classes now?
Yes. Yes, just among the new classes. Okay, so the key idea of few-shot learning, again, is that instead of directly learning how to classify the images, we try to learn the similarities between samples belonging to the same class and the dissimilarities between samples that do not belong to the same class. So instead of learning the classification itself, we'd like to learn we'd like to learn how to learn the classification. So under the hood, when you train a CNN model, it tries to learn how to separate the different classes from each other. It tries to understand what are the features that if it applies on the images, it will result in a good separation between the classes such that it can put its finger on one of those classes when you feed an image into the model. So in that case, we're only looking for the class. In this case, we want to learn how to learn the classification. This is why few-shot learning is also considered a subcategory of meta-learning, learning to learn, not learning to classify. So the question is, how is it that the model learns? Previously, we didn't really care too much about this. However, in few-shot learning, we want to learn how the model actually learns based on the similarities and differences. Okay. So one algorithm, one particular architecture that can be used for few-shot learning is a Siamese network. And Siamese basically means a twin network, a network that has two branches or two streams of information that are exactly the same in terms of the weights and biases. However, we might feed different images through those different streams or different branches. Okay, so this is only one algorithm, one particular architecture that can do few-shot learning. We don't have to necessarily use Siamese networks, but this is one algorithm that implements convolutional neural networks in order to achieve few-shot learning. Okay. All right, so to explain how this works, first of all, we construct a new data set out of our previous training data sets. What we do is that we take pairs of samples together and we create two new classes. One class is called a positive sample class. The other one is negative sample class. Positive samples are images that belong to the same class, and we give them a label. For example, here, we give them a label of 0. Negative samples are pairs of images that do not belong to the same class. So some pairs, similar, belong to the same class. Some pairs, not similar. Okay, and the purpose of this is for the model to figure out what are the similarities, what are the dissimilarities. Okay. Now, how can we use this to basically learn those similarities and differences? Okay. So far in the course, I have told you quite a few times that neural networks kind of compress the information that they receive, and they make new representations for the data points, new representation for images. For example, in a convolutional neural network, you feed in the image, and then after several layers of convolution and everything, you get down to, for example, 100 features at the end. So the network has figured out, okay, this image can be compressed down to 100 dimensions, 100 useful features, and if you do that, you'll have a representation that is amenable to classification because it's highly separable among different classes, so you can do classification very easily. And we have seen an example of this in the previous lecture where we used the CNN as a feature generator, and then we used logistic regression basically, and it works quite well. So neural networks create internal representations, meaning that they take the data, they take them to a different space where the information is more digestible, more understandable in terms of the classification task that we have. Okay, so an interesting application of this representation space, of this hidden space, is that in this case of problem of similarities and indifferences, we can say, okay, so how about we try to pull together the samples that they look alike in that hidden space and push away samples that do not look alike in that same hidden space. Okay, so we train the model in a way that if it sees positive samples, it tries to pull them together in that hidden feature space. And if they are negative samples, they do not belong to the same class, it pushes them away from each other. Okay, so kind of creates distance between negative samples and removes distance between positive samples. So this hints at a particular way of designing the loss function. And for this purpose, we use what's called a contrastive loss function. So it does exactly what I just described. So for example here, if y is the label of those positive and negative samples, 0 or 1. So for example, for positive samples, the label is 0, meaning that that second term becomes just 0, and then the first term becomes just d, and d is the Euclidean distance between the two feature vectors of those two images. So we have compressed those two images down to a vector, basically each one of them into a vector, and now we can just compute the Euclidean distance between those vectors, right? We can do that between any vectors. And okay, now that we have computed that, that's the distance between those points, right? Okay, so that's our loss function. We say try to minimize this distance, right? It's a distance between two points in a high-dimensional space. Try to minimize that for positive samples. For negative samples, it's a little bit more tricky. So in that case, we want to push them away, okay? So we have a function like this that you can see on the right-hand side. For negative samples, that left-hand side term becomes 0. The right-hand side term, however, that d still computes the distance between the points, okay? And if you take m to be a positive number, let's say like 10, for example, then this term becomes max of 0 and 10 minus d, okay? So it means that if the distance between those two feature vectors is smaller than m, then we will have a positive value. Then the maximum of that 0 and positive value will be the positive value. So as long as those 2 points have a distance lower than m, then they will be pushed away from each other. Does that make sense? Yes. Yes, m is like a hyperparameter. So this decides what is the margin between the margin that we want to have between those points. How far do you want to push them away?
I'm just curious, like, how similar or different are the negative samples, or how does that affect the training? So in this case, we have like a car and an elephant, which is very different. But in the case we're trying to like differentiate like species of a flower or something like that, how does that affect the training?
Yes. So the thing is, there's an implicit assumption about these similarities and differences. If you know that your fuchsia learning model is going to be applied on unknown classes with unknown images, that might not work too well. You kind of have to know that the structure of those images kind of looks alike. The problem is just that you don't have the same classes. Okay, so you have a trained data set on a bunch of animals, but you have new animals in your new prediction problem. So yeah, that works with fuchsia learning. But if the structures are vastly different, no. Yeah. Okay, so again, the purpose of the contrastive loss is to pull together positive samples and push away the negative samples that we have, so as to create distance between them. Okay, so this is a particular type of loss function. Yes?
Do we have like cases of overfitting in lower values of m?
Okay, if you choose the value of m to be too small, then the distances will be too close, and that basically doesn't achieve what you want. If you make it too big, however, then again this degrades the model performance. You don't want to push them too far away. It just messes with the quality of the model. Yeah, so there is a sweet spot in between.
Is the max expression there max absolute value or max on a number line?
No, it's just a max of numbers. So d is a positive number, m is a positive number.
So if you have a really large d, they're very different.
Yeah.
And m is in 10. Wouldn't that, so like say d is 100 and m is 10. Wouldn't that give you minus 90? It would go to 0 and then you have less loss.
It would go to 0 because in that case you already achieved what you want to achieve. The distance is already very large, right? So the loss becomes 0, you don't have anything to do anymore.
Oh.
Yeah. Okay, so this is basically the idea behind Siamese networks. And in terms of implementation, so now that we know about the loss function, we can understand this diagram. So when we feed in a positive sample, we have two images that look alike, belong to the same class. They go, they are fed into the network through these two branches. These two branches of networks, they are fed different images, but the architecture, the weights and biases, everything is exactly the same, because we want the same function to be able to distinguish between different images and similar images. Distinguish between different images and tell us whether two images are also similar or not. So we want the model to be able to do both. Okay, so this is why we make two streams, we pass in those images, and we ask the model if it's a positive sample, try to pull them together in the hidden space. If it's a negative sample, try to push them away from each other. Okay. Questions about the structure of the model? Anything else? Okay. So in terms of explaining how the model works, this is basically it. In terms of code, however, this is an interesting example of a situation that you have to kind of customize the modules that you have in PyTorch. And this is kind of a part of the reason that I like to present this particular type of algorithm. In this case, you have to define your own dataset object. You have to define your own loss object. You also have to define, always have to define your own model, but you have to define a particular type of model that has a special forward method because you have two branches. Let's see how that works. So a dataset object is an object in PyTorch like the image folder thing that if you iterate over that, it's going to go grab the images and read them into your Python environment. Right? That's what the dataset object basically does. So whenever an iterator is applied on that, it should go in the dataset and take one image for you into your Python environment. So here, because in this example, in the example of Siamese networks, we need to supply two images at the same time and a new label that doesn't exist in the dataset, the output should look something like this. So we have a first image, a second image, and then the label associated with that, whether it's 0 or 1, because it's either a positive sample or a negative sample. So we have to kind of construct this particular data set type of object in order to retrieve two images for us from those folders. And then, based on whether they are in the same folder or not, it should give them different labels. That's the idea behind this function. It might look a little complicated here, a little messy. I didn't have time to really rewrite it in a better form, but this is what it does. So any dataset object in PyTorch has a getItem method, and whenever you iterate through that, what it does is that its job is to go and bring one sample from the dataset for you. That's its job. And how you define it, that's up to you. In simple cases, it's already defined for us, but in this case, we have to do it ourselves. So what I do in this case is that with a probability of 50%, I want to go and take positive or negative samples, okay? And then when I grab one image from the data set, then I will go and look for either a positive case in the same folder or a negative case in another folder. So as soon as I find that image, okay, I have done my loop, I have randomized it. As soon as I have done that loop, I have gotten the paths to those images, then I simply just read the images and then convert them to grayscale because of the model that I'm training right now. And then the rest of it is just returning the images. So the part that looks a little bit complicated is this one. And this is nothing but taking each image and then going into the folder looking for either similar images or different images. Once you get that image, you can just return it and then do transformations or convert it to grayscale, RGB, whatever you like, and then finally return it in this format. Okay? So this is how we construct positive and negative samples for this particular type of training. whenever you do, you train custom neural networks, these ideas about changing the way that the dataset object works, the loss function works, it's really, really helpful and can give you a lot of like new capability to do something really interesting. Okay, so that's about the dataset. About the model itself, so this part's just regular CNN that we're used to, right? So 2 convolutional layers, and then I flatten everything, and then I have a fully connected layer here at the bottom. So everything is completely the same because this is what I promised you in the beginning. Each branch is just a CNN model. Now, the important part is how we forward the information through the network, because I have to take one image, forward it through one branch, take the other image, forward it through the second branch, and then I have to do something at the end about it. Yes?
I'm not clear on the data structure here. So is the folder structure the same as what we have been dealing with before? Like
Previously, yeah, so the structure of the dataset object, previously we didn't define our own dataset object. We just used image folder, for example, from PyTorch. And that automatically took care of reading the images and assigning classes. In this case, because this is a particular application, we have to define it ourselves the way that we like. Okay, so we have a CNN here, fully connected layers here. However, in the forward pass, because we're going to have 2 outputs for this model, we have to forward each image separately through the model. So I have a forward each function here at the top. What it does is it takes each value of x, each image, and forwards it through the neural network. Okay, so that's what we have been doing so far. Take the image, forward it through the CNN. Okay. However, in the actual forward method of the neural network, we have to do this per each input, right? Because the image, the positive sample, the negative sample contains 2 images. So we pass each of them separately, and we make a separate output for each of them. Okay, because we eventually we want to compute distances between those outputs. So this is what we're doing here. So in my forward method, instead of having just one output, I pass both images through the neural network, and then I return 2 outputs because I want to compute distances. Okay, so if I run that, this is the structure of the model, not too important here. Now comes the contrastive loss part. So for the contrastive loss, it is supposed to implement what I described a little bit earlier. So it has to implement this formula, this one. Okay, just as simple as that. Okay, what it should do in terms of code is that the loss function should also have a forward method, and that specifies how the flow of information works for this loss function. So just like a CNN, we have a forward method. In the first part, I just compute the pairwise Euclidean distance. Just Euclidean distance between the outputs. That's what I wanted to do. And then afterwards, I have 1 minus label, which is 1 minus y, and then power 2 of the Euclidean distance, and then plus the other term, y, and then power 2 of the maximum between 0 and the, maximum between the margin minus Euclidean distance and 0. So this is just a kind of an exact translation of the loss function that I presented a little bit earlier. That's our contrastive loss. I get the 2 outputs from the neural network, compute the distances, and construct the loss formula that I had in the beginning. Right? Yes?
The 2 outputs from the neural network are both 2D outputs at this point, correct?
No. So just like any other CNN, it will be a 4D tensor. So the batch size, the number of channels, and the width and height of the image. Yeah, just like any other CNN.
Okay.
All right. So now if this is a helper function, let's take a look at the data set that I have here for you for this problem. So it's a data set of faces of employees of AT&T that is taken in 1990 or something for the purpose of image recognition tasks. So whenever you see a label of 0, those are images of the same person. Whenever you see a label of 1, they are different people. So What we want to do, we want to increase the distance between dissimilar people and increase similarity between the pictures that belong to the same people. Okay. All right, so the rest of it, similar to what we had previously. We define our Siamese network object like that, the contrastive loss, and I define a margin for that. The margin is a hyperparameter that I have to experiment with. And then our optimizer, the dataset object, the train loader with the batch sizes, so everything is the same. In the train loop, so this time, instead of computing just like a y value, this time I'm computing two outputs, okay? Right? Because the model takes in two inputs and gives out two outputs, right? And once I have those two outputs, now my loss function knows something about those two outputs. It knows how to work with those. So it takes those two outputs in and computes the contrastive loss. And then, again, loss.backward, optimizer.step. Okay. So let's run this, and the loss hopefully should go down. And it does, and if it reaches values around 0.1 or 0.05, that would be a good loss value based on experiments that I had with the model. And then I'll show you what the distances look like between similar images and between dissimilar images. Okay, any questions? Yes?
Once we're defining the forward method, we are entering two inputs, two images. And once we're defining the model, how do we enter those images also? Is it just for the method, or just also use it for definition of the model?
So whenever you call the dataset object, it retrieves a bag of two images along with the label. And then because you have access to that, you can feed it to the network using the particular forward method that you have, just like I defined. Yeah, yeah. Okay, seems like it's already okay. Okay, let me stop that. And now let's plot the loss function. Seems like it's going down. It's pretty noisy, but it's going down. And then in the evaluation phase, again, something similar to what we've done previously. We take one image. Here I take one image from the test set and then compare it to other images in the test set. So images in the test set have not been used to train the model. Okay, hopefully we'll get some nice results. Okay, so these two people are the same. These two images are images of the same person. So the distance is 0.6. These are not the same people, but they still look alike. So the distance is 3.3. Okay, again, these two people are not the same people. They're more, their faces are more different. So 4.68. Again, this is the image of the same person, 0.074. Again, yeah, that's a weird image, but all right. That's a distance of 4, and again, this is again a different person, 3.7, and again 0.5 for the same person, different person, same person. So the model has achieved the goal that we had in mind. It has decreased distance between similar examples and has increased distance between dissimilar examples. Okay, so that's about it for the details that I wanted to cover in this lecture. I didn't want to go too much into the detail, but this is basically the idea behind Siamese networks and few shot learning. Yes?
So once you train that, using that for, say, prediction of putting in an unseen image,
Yeah.
how does that exactly work? So do you have to go and compare all distance values to all images, or
Okay, suppose that this is, again, a face recognition system for a company. So the company has a support set that contains the images of all of its employees that are authorized to enter the building. And if there's a new person that's registered in the system and has an image in that support set, once it passes through the system, it says, okay, I find a match with a small distance between this image and one image in the support set, so I can allow this person to enter the building, for example. But if that person doesn't exist, then all of the distances are pretty big. So, yeah.
So it compares against every image in the support
Yes, yes, yeah.
And then in terms of like deciding what's a big distance, you would kind of go through something like a recall precision type analysis.
Yes, you have to resort to those kinds of analysis to be sure. There's a lot of other details that a lot of other things that should be taken care of in order to make this system reliable. But if your model is trained properly and quite well, then the loss should be very close to zero. And in that case, the instances that are similar have very, very small distances. Others have noticeably, remarkably larger distances, so it's not too hard to distinguish between those. Yeah. Other questions? Okay, let's take a few minutes of break, and then we'll be back in 4 minutes. All right. We're back. We are back. All right. Okay, so this person does not exist. Okay, this is a picture of a person that has never been born, does not exist. You can go to this website, thispersondoesnotexist.com, and then you generate pictures of people who have never had the chance to enter this world. Okay, so how does this work? All right. So there is a very interesting algorithm in the world of convolutional neural networks called generative adversarial networks. So far, what we have seen is that we have a training data set and we are given classes and we want to predict new classes, and today we learned how to predict classes that we have never seen as well. But how about a different situation? How about if you want to generate new images based on the information that you have already seen? This is actually, I don't know whether the mechanisms are the same, but it's very similar to having a dream. So we experience life every day, and when we go to sleep, our brain seems like to be coming up with some very weird ideas for our dreams, and it seems like just combining information and create some other experience for us during our dreams. So it's something a lot like that. So our brains try to generate some experiences for us based on the experiences that we already had. So this idea was proposed first time by Ian Goodfellow, which is one of the masterminds in deep learning. You can see the original paper here. And the idea was to have a neural network model, look at a data set of images, and then try to train it in a way that could come up with new images. So this is a different type of model. It's not predictive model, it's a generative model. I don't know if in your statistic courses you have encountered generative models or not, but basically in statistics as well, you have some distribution. If you have the distribution, you can sample from it, so generate new data from your distribution. This is kind of similar to that idea. So the idea was that, okay, we have a data set of images. We don't have any labels. It's just images, okay. So can we generate new images based on that? The answer is yes. And the way it works is that there is a model, this GAN model has two components. One component is a discriminator or a judge or a critique, and one component is a generator. So there is a constant competition between these two components. The generator component generates new images out of nothing, out of randomness, and then it shows it to the discriminator. And the job of the discriminator is to tell whether this is actually a real image that could be in the data set, or if this is just something fake that has been generated by the generator. I mean, these days we have ChatGPT, so this is again a relevant question, whether a piece of text has been generated by the model, by a generator, fake generator, or it was actually something that was in the data set exactly. So this is the idea behind generative adversarial networks. And the word adversarial originates from this fact that there is a constant battle between these components in the generative model. This is, GANs are categorized as unsupervised learning tasks because we don't have any labels. We just have a bunch of images, and we want to learn a model, develop a model such that it could generate new images that look like the images that exist in our data sets. Okay, so this is again an example that I pulled from that website. All right, so in terms of architecture, this is what the architecture of a GAN looks like. So we have the generator part, the discriminator part. So with the generator, we have something that I discussed previously. We have a latent space of features. So in this case, that latent space is filled with random values, but when we feed it to a deconvolutional network, not a convolutional network, it kind of does exactly the opposite of what a convolutional network does. So in convolutional network, you take an image, convolve over that, and compress it down to the level of a vector. And for a generator, it's exactly the opposite. You take a vector, and then you expand it, and you expand it, and you expand it until it becomes the size of an image, looks like an image. And then once you have that generated image, you can give it to the discriminator, and that's a CNN. That's a regular, conventional CNN. And you pass that to that CNN, and you train it in a way so that the CNN, the discriminator, is able to tell whether it's a fake image or a real image. Okay, so a basic classification task, 2 classes. All right. So let's see how that works. So far we have seen these convolution layers. Again, their job is to downsample the input features. So we have an image, we want to compress it in order to have a representation of that in a lower dimensional space such that we can benefit from it for classification or any other task that we have. However, the opposite of this will be what's called deconvolution. It's not a great name, deconvolution, because it's not exactly the opposite of convolution in mathematical terms, but it's also called transposed convolution. So you can see that we have a smaller size image in terms of its dimensions here, and it gets expanded to a larger image. So that's the opposite, kind of the opposite of what a convolutional layer does. So that's the core component of the generator, because it takes small vector as a lower dimensional vector and expands it to higher dimensions in the form of an image. So this does upsampling instead of downsampling. So in this example here, we have 2x2 input, and we have a kernel for a transposed convolution. And then the way that it upsamples that input is that in this particular example with this particular specifications, it puts the kernel on top of each element that we have, and then multiplies that element by all of the elements of the kernel, okay, as you can see here. So everything becomes 0 here. Here we have 1, so everything just comes back as the kernel itself. For this element, everything is multiplied by 2 and then added, everything multiplied by 2, and then here everything multiplied by 3. And then finally, all of those results are added together, just like what we had in convolutions. So you can see that we've gone from this input size to this output size, which is larger. This is 3x3. This was 2x2. Again, here we have another example. So if it was our job to basically design these kernels to come up with kernels that could give us a nice-looking image that exists in the data set, that would have been a pretty tough job, maybe, impossible job, I guess. However, the idea here is that we design the architecture of the system, of the generator, of the GAN, and we let the model learn what are the kernels, the filters that have to be applied in the deconvolutional layers in order to generate a nice-looking image. So through back propagation, we learn what are the weights and biases that have to be in that kernel in order to, when it's passed over that image, when it upsamples it, it generates something that makes sense. Questions so far? Yes?
What if we have some max pooling and drop in our convolution layers, then we want.
So the convolution layers, like the discriminator part is kind of, in structure-wise, is totally separate from the generator. So those don't interfere with anything that's happening in the generator. And the generator, yes, you can have max unpooling. We won't discuss that here. It's kind of the reverse of max pooling. But these are kind of separate, quite separate, yes.
The architecture you showed above looks quite symmetric between the discriminator and the generator. Is that generally the case?
No, not necessarily, no. Because the only thing that matters is that we create an image that is something that the discriminator can process. That's the only important thing. Okay. All right, so how can we train again that I just described to you? First of all, we train the discriminator. And how we do that is that we generate some fake images in the beginning with the generator because we have come up with this architecture. So it's not trained yet, but that's all right. So we generate some fake images with that. And once we have done that, because we know that this is a fake image, so we have its label. And we also have access to the real images, and we have those labels. So this is a binary classification problem, right? We can create a data set, feed it through the discriminator, and train it so that it can distinguish between real and fake images. Yes?
Does the backpropagation happen all at once, or is it kind of two separate processes?
No, it's different steps, different processes, and I will show you in terms of code how that happens in detail. Yeah. Okay, so training the discriminator is not hard. We have real images and fake images. We know the labels. We feed them to the discriminator, and yes, it can be trained. Yeah, sure. And about training the generator. Now that the generator has to become better and better at generating images that could actually fool the discriminator into thinking that this is okay, this looks like a real image. So they have to compete with each other. In the beginning, the job of discriminator is very easy because the images that the generator is producing are looking like just noise. They don't look like anything that exists in the data set. So it's a fairly easy job. But then as the generator becomes better and better through this training process that I mentioned here, it will be harder and harder for the discriminator to detect fake images. So for the generator, we generate images and we label them as real. And then we pass those fake images with the real label through the discriminator for the judgment or the probability that comes back. And then we pass that judgment through a loss function. And we say, okay, so how far are we from the point that we can completely fool the discriminator? So the goal here is to generate something that could lead to a good probability in the discriminator. Okay, so that's the goal here. That's what the loss function has to do for the generator. And then we do backpropagation based on that loss function. Just do backpropagation and see what are the optimal parameters. Again, another diagram here. We start from random noise for the generator, generate an image, a fake image, and then we have the discriminators. So we have the real data set, feed both in, and detect whether one is real or is fake. Yes?
So for discriminator, we just train it once.
No, because the discriminator in the beginning does not have a hard job to do. So if you just train it for one epoch and then leave it like that, then it's not a very capable discriminator. It has to improve and get better and better because the generator is getting better and better. Okay, other questions before moving on to implementation? Yes?
What's the purpose of labeling the fake images as real when we generate that from the generator?
Oh, okay. So we want to label them as real and pass them to the generator to see what is the loss value generated for that if the discriminator thinks it's a real image. And then, based on that value, we want to improve what the generator should be doing in the next epochs. Yes?
So when we're doing that, do we also need to be passing real images to the discriminator as well to make sure we're not making it less likely?
Yes, absolutely. So this is what I said for the discriminator part. So when we create kind of the data set for the discriminator, we have real examples from the training set, and we label them as real. and we have fake images generated by the generator. So we have these two classes. Yeah. So it's constantly checking against the data set. Yeah. Okay. So I've used a data set called Faces dataset, and I have put the link to Kaggle. And if you want to play around with this, I think you all know that you have to upload your notebook to Kaggle if you don't have a GPU, because it takes quite a while to train GANs. All right. Okay, so I don't have the data set here, but here is sample training images that we have, just images of faces. And the goal here is to create a GAN that could generate faces that do not exist in the data set, but they are pretty acceptable. Okay, let's focus on creating the generator. So as I told you, this concept of latent vector, latent space, latent features, or hidden features come up quite a lot when you work with GANs or any models that works with embeddings and representations. So with the generator, you start from a latent vector, and originally you can give it a size of 1 by 1. This could be something else, but usually this is what people start with. And then it has, again, an arbitrary number of dimensions. Okay, so it's something like an image that has been compressed down to a level of a vector, basically. Okay, something like that. And whether it has 20 channels, whether it has 15 channels, it's something up to us. It's something that we have to decide. And then once we have that, we use the deconvolutional layers or the convolution transpose layers in order to expand that hidden vector, hidden latent vector to the size of an image. Okay, so we start from the vector, and then we expand it to a full 128 image. And so a couple of details here. It's empirically, it's been shown that it's better to use leaky ReLU because it guards against the problem of dying neurons. Because with ReLU, you have that region of 0. When a neuron hits that region, then it dies and it cannot be recovered. So we use leaky ReLU, which has a small slope in the negative area. And then this argument in place true just helps with doing the mathematical operations in place so that we don't occupy too much memory, because it matters in these large models. And then this is the architecture. So what we have here is that we take in the latent vector from outside. Okay, that's just the input to the generator. This is why you see latent size. That's the number of channels of the latent vector. And then we start expanding it. So here we're creating 1024 channels out of it, and then we're expanding it to the size of 4 by 4, for example, here. So 1024 channels, 4 by 4 image. And if you follow these modules here, these conv transpose 2D, you can see that the image is getting larger and larger progressively. So 4 by 4, 8 by 8, 16 by 16, all the way up to 128 and 128, and finally a tanh applied on top of that. Okay, so the main idea is just the convolution transpose 2D. And it's called convolution transpose 2D because this operation that it's doing in terms of matrix multiplication looks a lot like a convolution. When you do the operations, you have to take the transpose of something in between. That's the difference between a convolution. This is why they call it conv transpose. Okay, so that's the generator. And the discriminator is, at this point, this is should be pretty familiar for everyone. It's just a CNN, conv2D, batch norm, leaky ReLU, and yeah, all of the usual stuff. Okay, flatten everything, sigmoid, and yeah, I know, I've used sigmoid in the structure of the model. This is probably not a good idea. I should have changed that. This is from last year. Okay, so we have this. This is just a classifier, and then this is the structure of the generator and discriminator, and then in terms of initialization, so this is how we can initialize the generator. We give it the latent size, and as soon as it knows that, it knows what is the size of that latent vector, and it starts expanding that. For the discriminator, it doesn't take any arguments, just like any model, like any CNN model, you just initialize that. And then moving to device, creating the loss function, creating different optimizers for the generator and for the discriminator. Okay, It will make more sense once I show you the training loop, why we have different optimizers. And again, based on empirical evidence, we know that initializing those weights and biases with normal distributions usually results in better convergence. All right. So this is the important part. So as you can see, I am generating a fixed noise at the top, and this is for me to follow what the model is doing and what it's learning. So the GIFs that you see, that the image is kind of evolving as the model is being trained, it's the evolution of the results of passing this fixed noise to the generator to see what kind of outputs or images we get out of the model. So this is just to follow the training loop. Okay, so here, again, these are just a bunch of bookkeeping stuff, not too important. We have our main epoch loop. Okay, again, regular stuff. We have our mini batches, and here comes the important part. So step one, you have to train the discriminator, and how we do that. So first of all, 0 grad, all right, and then moving things to the device. Now we said that the images in the data set are going to be called real images, and the ones that are coming from the generator are going to be called the fake ones. So for real labels, I'm going to use the value of 1, and we have to create that tensor of ones ourselves. This is what I'm doing here. So I just create the labels, basically. Okay. Now, in order to get a value from the discriminator, just like the previous models, I have to pass the real batch of data into the discriminator, and this is the data that's coming from the data set. So these are real images existing in a data set, and I have just created the real labels, as you can see over here. So those are just ones. Okay. So this is one part. This is the real part. The discriminator has to understand that these are real images. Okay. Some bookkeeping, not too important. All right. Now comes the part that we have to generate an image using the generator. So I start from a random noise, and this is usually how it works because we don't have any understanding of what happens in the latent space. So we just start with a random noise, just like if we have a distribution in our statistics courses, when we want to generate some new values, we just pick randomly from that distribution. This is the same thing. Okay, that's our noise. Now pass the noise to the generator. All right, so that generates a fake batch of images for us. In this batch, all of the images are fake. All of them are produced from a random noise at each mini batch. Okay, and their labels should be zeros because they're fake. All right, and now that I have my fake images, I am in a position to feed them in the discriminator. So the discriminator has already seen real instances. Now it's time for it to see the fake instances. So here, I'm doing fake batch.detach, and I'm doing detach because at this point, I'm not trying to optimize the generator. The generator is acting just like a simple function. You pass it some noise, it gives you some image. Okay? So at this point, I'm not interested in any gradients that's happening inside of the generator. I'm not trying to optimize the generator at this point. So pass in, those fake images are generated, detach them from computational graph, pass them to the discriminator, and that constitutes the second part of our loss. So the loss of the discriminator is two parts, the loss of the real values, the loss of the fake values. And we just add them together, loss real, loss fake, and then do dot backward, and finally make one step using those gradients that have been computed.
Okay, just so I'm understanding correctly, that dot detach step, you do that just to save a bunch of time so that you're not computing unnecessary gradients?
That's right.
But it would still work.
It should still work. Yeah, because we don't need them, so we detach them, but it should still work. Yeah. Okay, so yeah, this is regular CNN stuff. The only difference is that we pulled real examples from the data set and fake examples from the generator. All right. Again, more bookkeeping here. Now we want to train the generator. So we want the generator to get better in generating images that can fool the discriminator. Okay. So generator.0grad, typical stuff. Now we pass the fake patch through the discriminator. That generates an output for us, meaning that it gives us a probability of what the discriminator thinks of this fake patch. Okay? And then, once I have that's the ideas of the discriminator, I put it into the criterion for the generator and say, okay, this is what the discriminator is thinking about our fake batch. Make it as close as possible to the real labels. Okay, this is the discriminator's idea. He's a little bit suspicious. Make those results as close as possible to the real labels. And once we do that, just do backpropagation to find out what is it that makes the discriminator more happy, right? Okay, and then dot backwards, optimizer g dot step. Questions? Yes?
Isn't it fairly common to train a generator with more steps than a discriminator? Like five time training the discriminator.
Probably you could do that. I haven't seen it, but you could try it out. I haven't tried it. Yeah, but it seems reasonable idea, yeah.
So at each epoch, we are generating more fake images with our generator initially, and then passing them to our discriminator, and then compare the result of the discriminator with the training stage of the generator. So if we go through more epochs, we are generating more fake images.
Mm-hmm. Sure.
Does that cause any class imbalance here?
No. So you generate more fake images. Okay, so the
We're adding more.
you always pull real data from the data set and you generate as many fake images as you have pulled images from the data set. Yeah, so it's always the same. Always the same, yeah.
In theory, for large numbers of epochs, you're running the same image through it multiple times.
Sure, yeah.
Data set.
Yeah, just like any other CNN that you do more epochs, the same images get passed through the model several times. Yeah. But the thing is, if everything is just right, then you will see that the discriminator and the generator are kind of fighting each other. So one gets a little bit better, the other also gets a little bit better, and they kind of just dance around each other. So it never happens like you have a full convergence of the accuracy of the generator of the discriminator. I will show you a plot of that. Okay, so the rest of it, yeah, not too important. The rest of it is just taking care of that fixed noise, generating some output so we can visually see what's going on. And if you actually look at the training process, this is the loss value for the generator and for the discriminator. Yeah, the loss of the generator is high in the beginning, and then it goes down, and they kind of reach a steady state. But the more interesting thing is this plot. So this is the probability that's being outputted by the discriminator. So in the beginning, the probability or the idea of the discriminator about a fake image being real is really low, right? So the model cannot be fooled. When you pass it a fake image, it says, no, this is fake. This is not real. The probability is very low, okay? And the probability of reals are very high. The probability of the discriminator saying that this is real is very high because it says the image from the data set is, yeah, that's the real one. Okay, but as time passes, you can see that it becomes harder and harder for the discriminator to tell whether an image is fake or not. And you can see that the generator at the same time is becoming better and better at fooling the discriminator. So this is kind of what usually the convergence history of a healthy GAN looks like. Sometimes you see this and then things start to diverge. That's when one of them, for example, if the discriminator overpowers the generator, it becomes so good again, so that the curves diverge, and then again we reach the original state. The discriminator is so good that at one glance it says, okay, this is real or this is fake.
But that sounds like a problem. But is it a problem in terms of image generation? Because sure, you have a really, really smart discriminator, but your generator is also still getting better, still trying to beat a really good discriminator?
Yeah, so the thing is, yeah, you reach a point that the generator cannot become any better. It doesn't have any idea how to fool the discriminator anymore because the discriminator has become so smart. You cannot fool it, basically. It's
We're trying to fool people, like regular people, like this image isn't like it's still a face, right?
oh, sure, sure.
Right, so like it's fine if it does that.
Yeah, yeah. I mean, sometimes, yeah. Maybe you have a divergent loss history. Everything looks like broken, but if I show you that image, you might say, okay, this is real. Because the model understands more features than just visually looking at the colors, as we have seen so far. So yeah, that's totally possible. And in general, for your lab as well, training GANs is really tricky. There's a lot of empirical understanding that goes into it for different types of data sets, different type of problems. It usually takes quite a bit of experimentation to get it to work. And this is not state of the art. So these days we have other more sophisticated models, like ideas coming from transformers that you will get familiar with in other courses, and also algorithms like stable diffusion and stuff like that. They are way more complex, way better at handling these things. So the interesting thing is that these GANs are not only applicable to images, they can actually generate like real, for example, physical data. If you train them on large enough data sets, for example, of the velocity, pressure field, temperature field in this room, then given certain constraints, you can actually generate new data. Given, for example, if you change the architecture of this room, it can still generate the real distributions for you. And this has been an active like area of research. So it's not just images, it's for any kind of data, basically. Okay, and if I show you what's... this is my best result out of the... Yeah, the images get quite scary at some points, actually. Yeah, I don't train these models during the night. Usually I do that in the mornings. Yeah, because that's not a pleasant sight to see, yeah. Yeah, and this is actually something that happens if... do you have any experience with DALL-E, the stable diffusion model? Yes. Yeah, you give it a text prompt and then, yeah, okay, I can actually show you something that was developed by Google, and it's called Deep Dreams. So some of these images look really weird and sometimes frightening. So again, this is like something that's done by our brains during dreaming at night. Yeah, so weird ideas like this getting combined together and, yeah, leading to weird images like these. I mean, I've seen worse. These are the best ones. Yeah, something like this. This is, yeah. Yeah. Oh, this one's good. Yeah, so all of these are generated by the same type of algorithms that we learned about today. The basic principles, concepts are kind of the same, but yeah, they have gotten way better at doing really interesting stuff. Okay, so that concludes this course. So in this course, what we mainly covered, if I want to summarize it in a couple of sentences, is that neural network models are models that are super flexible because they're made out of composable pieces and components. And why this idea works these days so well is because these days we know how to differentiate these composable bits when they're attached together using automatic differentiation. And when we have the gradients, we can compute the best values, optimum values for parameters to fit our data. And that's been that has played a huge role in the success of these models. And this flexibility is what leads to being able to be creative with these architectures and do pretty much anything that you like. If you're just curious and you have the energy and time to try new ideas. So I tried my best to include the stuff that I wanted to improve from last year. For example, this Siamese network was new. A bit of automatic differentiation was new. But still, there's obviously a lot of room for improvement. But I've tried to do my best. I hope you enjoyed it. I hope you learned something useful that you will use in your days to come in your data science careers. And on another personal note, I will be leaving MDS and UBC at the end of this block when I finalize the grades for this course. So it's tough. I've enjoyed my time a lot in MDS in the past 2 years. But yeah, life goes on, new challenges, new opportunities. So yeah, thank you everybody. Thank you and good luck with the rest of your MDS studies and your data science careers.